Okay, so good afternoon, everybody. We're going to start for today. Oh, hang on, Jack. I got a quiz for you, I think. No. I got a quiz to give back to you. So you still haven't taken quiz 2?
No, we can't take it after today?
Yeah, sure.
Okay, thank you.
Okay, so some announcements before we start. Today we're going to try to finish 1.8 and 1.9. So after that I should be just about 1 day behind. So I'm slowly catching up. Homework 1.6 through 1.9 is due on Tuesday. Okay, so after today we should be done with 1.9. So you've got Friday, Saturday, Sunday, Monday, and Tuesday to finish up that homework. Okay, so lots of time. But make sure you start early because it's 26 questions. It's a little bit longer than the last one. Okay, if you just do like 2 or 3 questions a day, you should be fine. So that would be the way that I would do it, rather than trying to do 26 questions at like 9 p.m. on Tuesday, February 8th. That's not going to work. Also, you can come and work on homework with me during office hours or with Daria during SI sessions. Speaking of, anything to report on SI sessions? Okay, so we're good on SI sessions. Right. Yeah, all the homework should be doable after today's class. All right, any administrative questions? Oh, one more thing. I almost forgot to announce. There's going to be a quiz on Tuesday, February 8th. And you know when would be a really great time to study for your Tuesday, February 8th quiz? Would be from 8 to 8:50 p.m. in closed hip 350 on Monday, February 7th. So, if you want to learn some of those extra problems, up your chances for getting one of the ones that you've already learned how to do, that'd be a good way to do it. Or during office hours today.
What units are on that quiz?
So the way that the quizzes work is it'll just cover basically everything between the last quiz and now. So I think the last quiz was up to 1.5. So this next quiz will be 1.6 to 1.9, I guess. Yeah. Everything up to today's class, basically. Yeah, I'll write that down. 1.6 to 1.9. Those are the sections that I'll pull the quiz questions from. Okay, any other questions? All right, then let's start by talking about the warm-up problem really quickly. So last time we were talking about compositions, and by the way, the recording for the composition part got deleted off of YouTube just because I had some issue where I think what was happening was when my laptop screen was falling asleep, it would cut off my microphone for the rest of the video, and then YouTube's processing whatever didn't like that. So what's on YouTube is really just the first like hour of our lecture of last class. So what is missing is this composition stuff. So we learned how to take 2 functions and combine them to make a new function in a special sort of way. And we do it by plugging one function into another function, right? And what we were learning was we always want to work from the inside out. So when we see something like f of g of x, in mathematics, we go from the inside to the outside. So we start with x, we plug it into g, and then we get something, and then we get whatever that was, and we plug it into the f function. Okay, so in terms of our conveyor belt system, it looks like this. Okay, so x goes into g, goes into f, and then we get out our final product. Okay, so we practiced a little bit about how to write that out, okay? And we also practiced a little bit about how to do that with a table, okay? Another common way to ask questions about compositions would be with if I gave you a graph of here's the graph of f and here's the graph of g, then tell me what is f of g of 2 or something like that, okay? And then you'd have to find 2 you find the height of g at 2, and then you go to that height on the x-axis, and then you find the height of f at that point, and that would be how you'd do a problem like that. Okay, so all we want to do is just work from the inside to the outside. Any questions about that last thing that we were talking about in class last time?
For A on problem 3, would you just multiply the f of x function by 2 and plug that in?
Well, for this situation, what we want to think about when we have these parentheses is not a multiplication in this circumstance. Since f is a function here, when we write f of 2, what we really want to do is not a multiplication but a plug. Okay, so f is itself a function. So in this circumstance, what we would want to do is take the number 2 and plug it in for x in f of x. So if we did that, we would find out that f of 2 is equal to 3 times 2 minus 1, which is 5, right? So when we plug in f of 2 like that, that's what we get. But now what we want to do is we see that f of 2 is equal to 5, right? So what I'm going to do is I'm going to replace where I see f of 2 here, I'm going to write 5. So this is the same thing as g of 5. Okay? So now what we want to do is take that 5 and plug it into the g function, right? So in this circumstance, we would get 1 minus 5 squared, which is negative 24. Does that clear that up for you? Okay. Good question. Any other questions? Yeah, Hudson.
Do D.
Can I do D? Sure. F of x. Yeah, it's perfectly fine to plug a function into itself. But when we have f of x, okay, then what I want to do is plug the function in for x in f, okay? So here's how I would do that. I know that f of x is equal to 3x minus 1, right? So I could rewrite this expression as f of 3x minus 1, right? So I just replaced f of x by something that is equal to. And now what I'm going to do is, I know that when I write f parentheses something, what I'm supposed to do is plug in that something for x in the function. So that's exactly what I'm going to do. So my original function was 3x minus 1, but I'm going to plug in 3x minus 1 for x. So I get 3 times 3x minus 1 minus 1. Okay, that would be how I plug with parentheses in that circumstance, okay? Happy?
Yeah.
Okay, any other questions on this composition stuff? Okay, how about the warm-up? Did anybody make progress on the warm-up? Let me make some space here. Oops. I don't know what just happened. Oh god. Okay, wait, we can undo this. There we go. Alright. The height h in feet of water in a cylindrical tank is given by h of t equals 0.25 t. Okay, so they tell us that the height is a function of time. And then they also tell us that the volume of water in a tank is a function of height. So if we have volume, which is a function of height, and height, which is a function of time, then if we want to write v equals f of t, okay, then it's going to be a composition. So we want to write v as a function of t. And we know that v is a function of h, and h is a function of t, right? So this is how we're going to combine these two things to get a new function, right? So in our circumstance, okay, I know that v of h is equal to 25 pi times h, right? 25 pi times h. But I also know that h is equal to what? H of t. So therefore v of t is going to be equal to v of h of t, which is going to be equal to 25 times pi times h of t. I suppose what I should write here is that actually v is going to be equal to f of t. That's how they write it in the problem. They say that this function is called f. So v is equal to f of t, which is equal to v of h when I plug in h of t. Okay, so this composition is then going to work just like the composition from before, right? Where I see an h of t, I'm going to replace it by the function h of t. So in this case, I get 25 times pi times 0.25t. Okay, so that's a formula for the volume of water in the tank after t hours. Any questions on this one? Okay, if you started this warm-up problem and you got it right, then great job. If you had something different than what's on the screen here, then you might want to come follow up with me in office hours and just chat and see what went wrong so that we can address it as quickly as possible and as early on as possible, because this composition stuff is going to be really important later in the class. Okay, so a good little check for if you're on board with compositions. Any questions on problem number 4? The warm-up. Okay, if not, then we're going to move on. I'm trying to finish section 1.8 and 1.9 today, so we'll see. Hopefully I can get it all done. But let's see, where do I want to start? I think where I want to start is with these graph transformations, if I'm not mistaken. Okay, so one thing we want to always keep in mind when we're manipulating functions is the graph can be really useful, right? So sometimes when we have our algebraic equation, it doesn't always compute what's going on in our heads. Having a graph can be really useful. And all of the time in this class, we're going to be transforming functions which we already know maybe what the graph looks like. So I'm going to do a quick review of how we do graph transformations. Okay, so it starts with when we have a function f of x. Well, we want to understand how does the graph change when we take that function and multiply it times a constant. Okay? Does anybody know what's going to happen to my function if I multiply by a constant which has absolute value larger than 1? Everyone agree with shrinking? Well, which way are you shrinking? Left and right or up and down?
For a parabola, isn't it like, well, it's just in, right? Like,
Yeah, so you can think about it in two ways. You can think of it as a horizontal shrink, but more commonly, c times f of x, where c is a number larger than 1, is thought of as a vertical stretch. This is the more common way of thinking of it. Okay, so for example, what does it look like? Well, if we have f of x looks like this, then 2 times f of x might look more like it gets stretched. So the whole point is that the height of the function gets multiplied by this constant. So if the height of the function gets multiplied by 2, then every point on this parabola, its height is now twice as high as it was before. So the way that looks is it stretches this whole thing. Okay, it stretches it. Okay, and likewise, if the absolute value of c is less than 1, then this is going to correspond to a vertical shrink. Okay, so you imagine just taking a sponge and smushing it, right? You take the whole, if you draw your picture on a sponge and you smush it from the top and bottom, then it gets kind of longer in the left and right direction and shorter in the up and down direction, right? So that's what we mean by vertical shrink. Okay, and finally, if in addition c is less than 0, so if c is a negative number, then we are going to reflect our function about the not the y-axis, about the x-axis. Okay, so if instead we did f of x going to negative 2 times f of x, well, all of the heights of this function get multiplied by negative 2. So instead of looking like this, it would still be stretched, but it would also be reflected. Okay, it would also be reflected down to the bottom. Okay, any questions about vertical stretches and shrinks? Okay. Next up, what if I multiply by something on the inside? Let's go from f of x to f of c times x. What happens to the graph? Can anyone tell me what happens if c is larger than 1 in absolute value? Horizontal. And is it going to be a horizontal stretch or a horizontal shrink, do we think? Sorry? It is going to be a horizontal shrink. Okay, and this kind of leads into one major theme with graph transformations, okay, which is if we do something on the outside, okay, versus if we do something on the inside, okay, then the effect is sort of reversed of what we think it's going to be. Okay, so if we have c larger than 1 on the outside, it causes a vertical stretch. On the inside, it causes a horizontal shrink or compression. That's just another word for shrink. Okay, and if c is less than 1, then this is going to correspond to a horizontal stretch. Okay? So it's kind of like in Stranger Things when you go in the upside down and everything's all wonky. Okay, when we do stuff on the inside of the parentheses, then it's going to be kind of the reverse of what we think it's going to be. Okay, so also if in addition c is less than 0, then we're going to get another reflection, except this time it's going to be a horizontal reflection, okay? Think about a horizontal reflection goes left and right. That means we're reflecting about the y-axis. Okay, I know there's going to be a lot of writing today. Just bear with me. Number 3. Okay, so we dealt with multiplying. What about adding and subtracting? Well, let's talk about what happens when we take f of x to f of x plus a. Or we can just keep it plus c. Plus c for a constant. F of x plus c. Well, what does this mean? F of x is the height of the function. If we take the height of the function and we add something to it, what's that going to do to our picture? It's going to move it up, right? Okay, so if c is larger than 0 and we add something positive to our height, then we shift up c units. Okay, if c is less than 0, then we shift, quote unquote, up negative c units. i.e. shift down c units, negative c units. Okay, so if we subtract something from our height, it goes down. If we add something to our height, it goes up. Fairly straightforward. Okay, now comes the confusing one. Now we're going back into the upside down. Okay, so what about if we do f of x plus, or f of x, and we take that and we change it to f of x plus c, where we add it on the inside. Well, we said in the upside down, everything's going to be all wonky. If we think about adding something to a function, okay, if we think about adding something to a function, we would think, maybe, naively, that would move us to the right. Because on the x-axis, the bigger numbers are on the right. So if we add something, you would think that we go to the right. But we have to remember, when we're inside the parentheses like this, we're in the upside down, we have to do the opposite of what we think we should do. So that's going to give us a horizontal shift. Horizontal because we're inside. And rather than shifting to the right like we think it would be based on number 3, we're going to actually shift to the left. A units. Not A, C units. Okay, and then likewise, if c is less than 0, then we shift to the right by negative c units. Right? Negative c would be a positive number if c was already negative. Okay, or we could do not negative c, but how about absolute value c units? Okay, so if we subtract something on the inside, we're moving to the right. If we add something on the inside, then we're moving to the left. A little bit confusing because the bigger numbers on the x-axis are to the right. But we got to remember, when we're inside the parentheses, we're doing everything in this kind of funky way. All right, any questions about graph transformations so far? We're going to see an example here in a minute. All right, one more thing to talk about with graph transformations is the order in which you should apply them. So here's your rule. If we take f of x to a times f of b times x plus c plus d. So we have all of the transformations present here. We have a vertical stretch or shrink, a horizontal stretch or shrink, we have a horizontal shift, and we have a vertical shift. So all of the shifts and stretches are present here. We want to know what's the order in which we should apply them. And it goes like this. First, do the left and right shift. Secondly, do horizontal stretches or shrinks or reflections. Third, we do vertical stretches. Why don't I just copy, save myself some writing. Stretches, shrinks, and reflections. Oops, not cut. Come on. Copy. This wound up being more work in the end. Vertical stretches, shrinks, and reflection. And finally, vertical shift. Okay, so horizontal shifts, horizontal stretches, vertical stretches, and finally, vertical shift. Okay? All right, so that's the order. So let's see maybe an example here. Oh, yeah, okay, let's see a quick example, and then I'll go back to that. So quick example here, we have the graph of f of x appearing here. Okay, so this is the graph of the function absolute value of x, it looks like. Okay, because when x is 1, then it's 1. When x is 2, it's 2. But when x is negative 1, it's still 1. And x is negative 2, still 2. So this is the graph of the absolute value of f of x. And we want to shift it and turn it around in all sorts of different ways. So let's complete this one as a class. So let's look at a first. Well, f of x plus 1, what kind of shift is this going to produce for our function? Vertical shift, right? And it's a shift because it's a plus, not a multiply. Okay, so we get a vertical shift. 1 unit, up or down? Up 1 unit. Okay, so all we're going to do is we're going to look for a picture which looks like this one, but it's gone up 1 unit. Well, to me that looks like 3, yeah. Okay. So next up, we've got f of x minus 1 plus 3. So what transformations are present in part B? Yeah, we have a horizontal shift coming from the inside. It tells us to go to the right 1 unit. Okay, so right 1. And then this next part says up 3. Okay, so we just want to go to the right 1 and up 3. I think that's this one here, right? You went to the right 1 and up 3. So that's 5. We don't have any stretches here. That's kind of annoying. Oh well. All right, I think we can get the rest on our own. So do the rest on your own. Okay, but before I move on to section 1.9, I want to talk about one more thing, okay, which is the graphs of very common functions, okay? So if you're following along in the notes, you're going to need an extra sheet of paper or two for this. I just want to, yeah, go ahead, Jack.
So for the example that we just did,
Yep.
there was no instances of like what when you mirror it, pretty much. What's that called?
A reflection?
Yeah. What does that look like actually written out if it were to be a reflection?
Well, let's try f of, okay, how do I want to do this? Well, let's try f of negative x, right? What kind of reflection is this going to produce? A left and right or up and down?
Left and right.
Left and right, because we're inside. Every time we're inside the parentheses, we're always dealing with left and right, horizontal, okay? So I guess if you think about what that would look like for our graph, what it would mean is everything which is on this side is going to get moved over to this side, right? But also everything that's on this side is going to get moved over to the other side, right? So if for a symmetric graph, if you do a reflection, it just looks the same, exactly. But say you had a graph like, a graph like this, and you wanted to do f of negative x, well, what it would look like is, let's see if I can draw it correctly. It would look like this, I think. See what I mean?
Mm-hmm.
So this point came over here, whereas this point went over here. Okay, so everything on the left gets moved over to the right side, and everything on the right side gets moved over to the left.
Thank you.
Okay, yeah, no problem. So let's do some quick graphing skills. All of this should technically be review, but I just want to go over it one more time so that if you don't remember some of these, you can study these like flashcards or something. Okay, so what does it look like if we have a function which is a constant? Well, a constant function is nothing but a linear function with slope equal to 0, right? If we plug in m equals 0, then we get f of x equals b, just a number. So a slope which is 0 means we have no rise but lots of run. So it's a horizontal line. Okay, so horizontal line. at height c. Okay, then f of x equals mx plus b. We know well that this should be a line, right? So this is going to be a line. It passes through b, and its slope is m. Okay, so slope indicates how quickly the line is rising or falling. Okay, we're going to do these kind of rapid style. So next up is f of x equals x squared. We all know that this looks like a parabola. Okay, parabola. So as x gets larger, x squared will be even larger than that. Okay, because as we go forward, first we do 2 times 2, then 3 times 3, then 4 times 4. Okay, all these numbers are getting bigger and bigger and bigger and faster and faster and faster, which is why we get this parabola shape. Okay, but there's something funky about x cubed, which is a little bit different. On the right-hand side, it looks a lot like x squared. As we go forward, the numbers get larger and larger and larger, right? We go 2 times 2 times 2, 3 times 3 times 3, okay? It does grow a bit faster, but it looks kind of similar. How about the left-hand side? Yeah, it's going to go downwards, because if I take a negative number times itself 3 times, then you get a negative times a negative. The first two cancel each other out, but the last negative makes it negative again. So it looks like a parabola, sort of, but upside down. Okay, so you get this, well, I didn't draw it very symmetrically, but you get this kind of shape like this. Okay, then f of x equals absolute value of x. We just saw that one. It looks like a V. Kinda. Okay, f of x equals square root x. Something we gotta remember for a function like this is what is the domain of this function? Who can tell me what is the domain of f of x equals square root x?
0 to infinity.
0 to infinity, right? Because we can't do square roots of negative numbers. Well, we can, but we're not doing it in this class. So we take 0 to infinity with a bracket on 0, because square root of 0 is still okay, right? And it looks kind of like this. Okay, so that's the graph of square root x. Okay, how about graph of cube root of x? What's the domain of the cube root of x? Negative infinity to positive infinity? Yeah, so exactly. The cube root is kind of funny. We think, well, for square roots, we can't do square roots of negative numbers. But remember how we said that a negative number cubed is something negative? So if we have a negative number, to reverse that process, we're going to then again get back a negative number. So it's okay to do cube roots of any number, okay? And it looks like the square root function on both sides, except, of course, the cube root of a negative number will be negative, right? So it looks kind of like that. Okay, tricky, tricky. All right, what about the next one? 1 over x, what's the domain? Any numbers which are going to cause problems for a function like 1 over x?
0.
Yeah, 0. So, and that's the only one. So I'll just say x is not equal to 0. Okay, that's a perfectly fine way to write the domain. And what it looks like is, well, when x is really big, then 1 divided by x is really small, right? But what happens to 1 over x if x is really small, like something very close to 0? What happens to the number 1 over x?
It's big.
It gets big. That's right. So as we get close, it gets big. So it actually looks kind of like this on this side. And of course, if we think about, well, what happens to this fraction if we plug in a negative number for x? Well, the fraction is going to be negative, right? So it's going to look like this on this side. Okay, then f of x equals 1 over x squared is going to have only one small difference to the 1 over x graph. The only difference is, well, it'll be a little bit sharper of a picture, okay? So maybe on the right hand side it looks a little bit closer to 0 there. So it's steeper. But also something will be different on the left hand side. What's going to be different? Can't do it? What if I plug in -2? What do I get if I plug in -2 for x? Well, I square it, so then it becomes 4, and then I do 1 divided by 4, right? So the tricky thing about this one is, well, x squared, if I plug in a negative number, it becomes positive, right? So this one's going to look the same on both sides. Okay? Same on both sides. All right, now a to the x we should be confident with. We've been looking at graphs of this all the time so far, right? It goes through the points 0, 1, right? Because if I plug in 0, I get a to the 0, which is 1. And it also goes through the point 1, what? What should go in this blank here? 1,
0.
Not 0. Let's think about it. Okay, what does it mean if this number is 1? For the function, it means that the x value is 1. So if the x value is 1, how do I get the height of the function? I plug in 1 for x. So my question is, what is a to the power 1?
1.
Not 1. Just itself. Yeah, a. So it also goes through the point 1, a. Okay, good. So what about if a is less than 1? What's the picture going to look like as it compares to if a is larger than 1? What's the difference between these two? Sorry? Flipped over the x-axis. Not quite. Flipping over the x-axis is this one, right? So if we flip over it, then we would get a picture which would look like this, right? Which isn't quite what we're looking for. So let's think about functions like f of x equals 0.5 to the power x, something like that, or 1/2 to the power x. As x gets larger, what's happening to my number? It's getting smaller. So the difference between a larger than 1 and a less than 1 is a larger than 1 corresponds to exponential growth, and this one corresponds to exponential decay, which means it looks a lot like this one except backwards. The number goes from being really big to being really small. So it looks like this. Okay, and guess what? It still goes through the points 0, 1 and 1, a. It just so happens that a is a number which is smaller than 1, which means it's going down. Okay, and lastly, f of x equals ln x. Now remember we had that information that we know that ln of 1 is equal to 0, and we know that ln of e is equal to 1. So if I put 1 here and e here, at 1 it's 0, at e it's 1. And in fact, it's going to be negative immediately before that and go up kind of like this. So ln of x looks a lot like e to the x if we were to flip it about the line y equals x. So this is the graph of, let me change that color. Style. We'll make it pink. No, not pink. What do we want to make it? Green, maybe? Okay, so this is y equals x. And this is the graph of y equals e to the x. Then f of x equals ln x looks like if we shifted everything across this line. Okay, in fact, all inverse functions have this property that if you graph them, they look like they've been reflected about this line y equals x. Okay, so just to be clear, this is ln of x. Not very good at arrows. Okay. Any questions on all of these graphs? Okay, these are graphs which I would say are more or less mandatory to have memorized for the class. So I would, if you want to make some flashcards, you could do it like that, or if you want to just study this a handful of times from the notes, that's also fine. But I think you pretty much need to know what these functions look like in order for us to move forward with the class. Okay, any questions? Yeah, Brendan.
I'm just curious, is the graph for the cube, is the graph for this cube function similar to that of the tangent function?
Yes, but we are not going to discuss trigonometric functions in this class. If you want to do calculus with trigonometric functions, you need to take 141. Yeah, so that should make everybody happy, right? No trigonometry. Ooh. Well, it doesn't make me happy because I like trigonometry. Okay, well anyways, let's move on. I think I've said everything I want to say about graph transformations. There's some homework questions to help you learn this stuff on your own. So I want to move on to section 1.9 now and talk about, 3 quick things. Okay, so first of all, we're going to talk about power functions, which is a sort of weird mathematical concept. I've never heard of power functions except for in this class. But here's the definition. I guess it's sort of helpful when you think about polynomials. So q of x is a power function if q of x is proportional to a power of x, i.e., q of x is equal to k times x to the p, where k and p are real numbers, and k is not equal to 0, and p is not equal to 0. Okay, so we have a function q of x equals some number times x to some number. Okay? A crucial distinction here is if I add something, it's no longer a power function. Okay, so a power function is just a number times x to a number. A number times x to a number. This is what we call a power function. Okay, so let's see some examples here. Well, what do we think about y equals 1 over x to the 5? Power function or not power function, based on this definition? I'm hearing a lot of no's, but I think it actually is, and there's a trick to see how it is a power function. Does anybody see what it is, Hudson?
It's just x to the fifth to negative first.
Yeah, you could just say that this is equal to x to the negative fifth, right? So, Hudson, I guess you were in office hours the other day, right? When we were talking about
I was in what?
Were you in office hours when we were talking about exponents? Yeah, so the other day in office hours we reviewed exponent rules. So that's Hudson benefiting right there from that office hour session. So dividing by x to a power is the same as doing x to the negative power. Okay, and this looks like k times x to the p, where k is 1 and p is negative 5. Okay, so this one actually is a power function. But it was a trick question. All right, let's do another trick question. How about 14 times the 7th root of x? Okay, it actually is a power function.
To the power of 1/7.
That's right. Square roots and nth roots are powers of 1 over n. Okay, so this is the same as 14 times x to the 1 over 7. Okay, 7th root is the same as 1 over 7th power. That's the definition, actually. So this means that k is 14 and p is 1/7. So yes, it is a power function. How about 4 times 3 to the x? No, why is this one not a power function? There's a power right there, x. Yeah, what kind of function is this? Exponential, right? When we have the independent variable appearing in the exponent, then it's an exponential function. So this is not a power function. It is an exponential function. Okay. I'll leave the rest of them up to you all to try on your own at home, or come to office hours to see the rest of them. Okay, so power functions, there's really nothing to them. We just want to identify whether something is a power function or not by checking, well, is it equal to a number times x to some number? Okay, and if we've got pluses in there, if we have variables and exponents, it's all going to spoil this particular form. Okay, so you'll notice a lot of the time in this class, we focus not on particular equations, but on the form of an equation. Okay, so the last time you probably focused on the form of an equation was something like learning the quadratic formula, right? You think about quadratics as ax squared plus bx plus c, where a, b, and c can be any number, right? We're going to do a lot of that stuff where we just say, well, I don't know exactly what my function is, but I know it's quadratic. Or I don't know exactly what my function looks like, but I know it's a power function. And we want to come up with general rules for how we're going to manipulate these functions, okay? So in this class, we go from sort of high school math, which is a lot more specific, okay, to more general concepts. Okay, so let's talk about, well, okay, first of all, are there any questions about power functions? Yeah, Jack.
In that last example, if it had been 4 times 3 to the x and then x was raised to another power, like the power of the power, would that have been now a power function?
Like, if I put a square there?
Is that even possible or no?
Well, this is still a function, sure. You can plug in, you just take x, then you square it, then you use that as the power, right? But it wouldn't be a power function. If you look at just x squared, it's a power function. But if you take 3 to the x squared, well, a number to a power function does not make another power function.
I would.
Good question. Any other questions about power functions? I thought I saw one more. Yeah.
Yeah, so in a function that has a number, or not a number, but yeah, a number attached to a variable raised to a power, would that qualify as a power function even though the constant or the number in front of the variable is not separated from it?
Sure. So do you mean like part D you said?
Yeah.
Sure. So let's see part D. Okay, a lot of the times we can simplify these guys, right? Well, how would I simplify 2x to the 4th? Is there a way I can simplify this? Yeah, I put the fourth power on each one. This is the same as 2 to the 4 times x to the 4, which is the same as 16 times x to the 4. And now it looks like a power function. Okay, I'm going to move on for the sake of time, Brendan, but if you want to ask another question after class, hit me up, okay? All right. Next, I want to talk about proportionality. Okay, I already used the word proportional actually in the last definition, so I probably should have talked about this first. But we say that y is quote-unquote directly proportional to x if y is equal to k times x, where k is a number which is not equal to 0. Okay, so what does that mean? It means that basically y and x enjoy a linear relationship. Okay? Well, I don't know if they enjoy it, but they have it, right? So when x is 0, then y is also going to be 0. So this just means that their relationship looks like a line which passes through the origin, right? It looks like a line which passes through the origin. It might be steeper if k is big, or it might be not so steep if k is small, right? But this is the basic idea behind something being directly proportional to something else. Okay? And then we have sort of the opposite of this, which is we say that y is quote-unquote inversely proportional to x if, can anybody guess what the relationship is going to be based on this terminology and the previous definition?
K divided by?
Yeah, very good. It's going to be k divided by x. Okay, so rather than multiplying, we do sort of, I guess, what you think of as the inverse of multiplication. We do division, right? Okay, so what does that mean? Well, it means if x gets bigger, then y gets smaller. Conversely, if x gets smaller, then this fraction has a smaller denominator, and hence this number is a bigger number. Okay, so that's the way we think about this. So what does that look like? Well, it looks, on a graph, it looks like this, right? Oops. It looks kind of like that 1 over x, right? So this would be 1 over x. But if you had, say, 2 over x, it would look similar. It would just be a little bit more further out, right? But same general shape. Okay, you get the point. So this is what it means for two things to be directly proportional to one another and for them to be inversely proportional to one another. Okay, so let's see a quick example here. In this word problem, let me keep track of my time here.
Is k still equal to all real numbers? Which cannot be 0?
Yeah, so k is still just a number which is not 0. Yeah, just to remind everyone, this funny symbol here means belongs to, or is a member of. And then this other symbol means real numbers, right? So k is a member of the real numbers. So k could be any number like 0.1, 1 billion, negative 1 billion, pi, okay, any of those numbers, but not 0. Okay, any other questions about direct proportionality and inverse proportionality? Okay, if not, then we move on to this quick example here. So we have George is buying Wow, we've got a real-life watermelon problem here. George is buying a cart full of watermelons at the grocery store. The cost of his grocery haul is proportional to the number of melons he buys. Okay, so I'm going to immediately define two variables. C is the cost, and M is the number of watermelons, number of melons. It's just one L, right? Yeah, just one L. Number of melons that he buys. Okay, so these two things are directly proportional to one another. Okay, it says proportional. If it doesn't say inversely proportional, it means directly proportional. So we know that C is going to be equal to some number K times M, right? Okay, and what we're supposed to find out is what is the constant of proportionality. So our goal is to find K. Oh yeah, I should have probably mentioned in the previous part, the number K is called the constant of proportionality. Okay, it's called a constant because it's a number, and it's called the constant of proportionality because it governs this proportional relationship. Hence, constant of proportionality. Okay, so we have a C equals Km situation, and we're supposed to find out what K is. Okay, and we're given that the trip costs a total of $79.80, and George left the store with 20 melons. Okay, so we know that the cost is $79.80, so I'm going to set $79.80 equal to the constant of proportionality K times the number of melons, which is 20, right? So now I just solve for K. I divide both sides by 20. Okay, so K is going to be, let's see, it's almost 4. It's like 3 point, sorry?
3.94.
Thank you. 3.94. Okay, so we found the constant of proportionality. Let's, how do we interpret that constant of proportionality? In terms of the problem, what does the constant K equals 3.94 mean in terms of the problem? Very good. Cost per melon. Okay, so that's a simple proportionality problem. Okay, I don't want to run out of time here. This is another proportional one. You can do that one at home. Okay, I want to really quickly cover problem number 4, okay? Jen and Kyle are moving across the country. The reason I want to cover this one is because the time it takes to unpack the van is inversely proportional to the number of people, right? That makes sense. The more people we have, the less time it takes to unpack, okay? So if we know that we have two variables here, first is the amount of time it takes. Okay, and in this case, time is actually going to be the dependent variable, right? Because the amount of time that it takes is going to depend on the number of people we have, right? And let's just say the other one's P, which is number of people. Now, the inverse proportionality relationship means we get the time it takes is inversely proportional to P, which means that T is equal to K divided by P. Okay? So they tell us also that if it takes 6 people 4 hours to pack up the truck, okay, that tells us that when p is 6, t is 4, right? So we get 4 equals k divided by 6, right? Which means that k is equal to 24, right? Multiply both sides by 6. Okay, so we know that t is actually equal to 24 divided by 6. Not 6, 24 divided by p, excuse me. So if we want to answer the second part of the question, which says how long would it take 10 people to unpack the truck, now that we've found the constant of proportionality, all we have to do is use this relationship and plug in 10. Okay, and we find it takes 2.4 hours for 10 people to do it. Okay, so that's an example of inverse proportionality. Any questions on the inverse proportionality or on proportionality in general before we move on to a different topic? Yeah, Brendan?
So the graph for proportionality is essentially a linear function.
For direct proportionality, it will be a linear function. For inverse proportionality, it's
Like an exponential function.
not exponential, but it has the same kind of vibe as 1 over x, right? Which the graph of 1 over x is curvy like this, right? It looks kind of like that. Good question. Any more questions on inverse proportionality or proportionality? Jack, face mask, please. Thank you. Okay, then let's move on. So the last thing I want to talk about today are quadratics and just polynomials in general. Okay? So let's start with a quadratic. A quadratic function, q of x, has the form ax squared plus bx plus c such that a, b, and c are real numbers and a is not 0. Okay, so we have something like a number times x squared plus a number times x plus another number. Okay, it's okay for b and c to be 0, but a cannot be 0. Why should a not be 0 in a quadratic function if we have ax squared plus bx plus c? All right, let's have one person. Raise your hand. Yeah, Shania.
Instead of being quadratic, the a term will disappear. It will be
Exactly. The a term would go away. So it would be bx plus c, which is a linear function. Very good. Okay, so that's a quadratic function. And the next definition that we should give is for a polynomial, which is a little bit more complicated. A polynomial function, I'm going to do p of x for polynomial, has the form, and this is going to get a little bit confusing, not confusing, but it's a little bit tedious to write out. It goes an times x to the n plus an minus 1 times x to the n minus 1 plus dot 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 plus a1x plus a0, where a0 dot 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 to an are real numbers and n is an integer. If you want to know the fancy symbol for integer, it's z, like this. Why don't I say a non-zero integer?
So
And-
n can't be 0.
Yeah, n's not. Well, I guess 0 is a polynomial. And yeah, I guess n can be 0. It's fine. But it's not really meaningful. Okay, so what is the point? The point is we have basically a sum of power functions. Okay, each of these individually is a power function, right? An times x to the n. But don't forget that n is an integer. That means it's a number like 1, 2, 3, 4, 5. No fractions, no decimals. Okay? So all of these are power functions where our powers are positive integers. Okay, I should say, that's what I should have said. N is larger than or equal to 0. Okay, so positive integers. So something like 3x to the 5th plus 2x squared plus 1. That's an example of a polynomial. Okay? All right, knowing what polynomials are is going to be important later in the class. I know I keep saying that for a bunch of stuff, but it's true. So, what I want to communicate is that we should know how to identify a polynomial when we see one. Okay? So, for example, f of x equals 3x squared plus x to the 1/2. Polynomial or not polynomial? Seeing heads shaking no. I agree that it's not a polynomial. Can anyone tell me why it's not a polynomial? Sorry, I can't hear what you were saying.
It decreases by more than 1 in the exponent.
Yeah, there's a problem with the exponent. It's not necessarily that it decreases by more than 1. It's that this power here is not an integer, right? Let's think about it this way. If n is an integer, right, then n minus 1 is also an integer. And so is n minus 2, and so is n minus 3, all the way down to 1 and then 0, right? So all of the powers in a polynomial should be whole numbers. Okay, so this is not a polynomial. But how about something like 3x to the 5th minus 27x squared? What do we think? Polynomial or not polynomial? Yeah, this one is a polynomial. It's a polynomial where a5 equals 3, a4 equals 0, a3 equals 0, a2 equals negative 27, and a1 equals 0, and a0 equals 0, okay? So we just want to think about this in terms of the coefficients, right? The coefficients can be any number. The powers have to be positive integers. Okay, one final example of polynomials. How about this one? Is this one okay? Why don't we make it really crazy? How about pi x squared minus e? Challenge problem right here. Pi x squared minus e. Do we think that one's a polynomial? Well, let's check together. What should we have? We should have numbers times positive integer powers of x. Well, how about the positive integer powers of x? Well, first of all, I've got x squared, and then I've got the constant term. So my x powers are okay. And the other thing we need to do is that a0 through an, our constants, should be real numbers. So is pi a real number? Yes. Is e a real number? Also yes. So we have real numbers times non-negative integer powers of x. So we get a polynomial. So this one's yes and yes. But I just wrote that last one in a really kind of confusing way. Okay, any questions about quadratics and polynomials in terms of identifying them? Okay, then I think we can close for today. One final thing that I want to say is if you do not remember how to find zeros of quadratics, okay? That means factoring and using the quadratic formula. Please come to office hours. All right, have a great day and a great weekend. Yep, you too. Oh, Jack, you want to do your quiz, right?